This lesson will cover differentiation of functions, and to do this we use what's called the chain rule. You should already have come across functions like this and know how to differentiate them. So y equals 3x squared plus 4, dy by dx is 6x. But what if y is not given in terms of x, but is given in terms of u, and then we know that u is given in terms of x. So this is what I mean by a function of a function and why it's called the chain rule. We have y in terms of u and u in terms of x. Now we could approach this by substituting. If we've got y equal 4u plus 3, I can substitute u into here. So this would be 4 times x squared, take 4 plus 3, which is 4x squared, take 13. This is fairly easy to differentiate and results in 8x. The chain rule will give me a method for differentiating y with respect to x without first having to do this substitution. So the chain rule says that if y is a function of u and u is a function of x, then to differentiate y with respect to x, we find dy by du and multiply by du by dx. Now just a word of warning here, because it looks a bit like cancelling fractions. It's like dy by du by dx, cross out the du's and we're left with dy by dx. Now of course that's not what we're doing here, these are not fractions, but it is a helpful way to remember the chain rule because visually it does look a bit like we're cancelling fractions. In example number 1, we have y given as a function of u and we have u given as a function of x. So dy by dx is equal to dy by du multiplied by du by dx. So differentiating y with respect to u is 2u take 5, and we're multiplying this, so don't forget the brackets, by du by dx. The derivative of u with respect to x is 7. Now we haven't quite finished because we are looking for dy by dx, which remember means the derivative of y with respect to x. So my final answer needs to be given in terms of x. If I simplify this, I get 14u take 35, but remember u is 7x take 3, so this is 14 times 7x take 3 take 35. Now just a note here on function of a function or composite functions. If I want to find y when x is 2, I first need to find u and then substitute u into y. So given that x is 2, we'll use the same functions as before. U is 7x take 3, 11, and then to find y I need to square u and subtract 5u, 66. Now the chain rule can be extended, so instead of just having function of a function, I've now got function of a function of a function. We've got y in terms of t, t in terms of p, p in terms of x. And I'm looking for dy by dx. So a variation of the chain rule, dy by dx is dy by dt multiplied by dt by dp multiplied by dp by dx. So I need to differentiate each of these functions. dy by dt is 6t, dt by dp is 5, and dp by dx is 6. So this is 180t. But again, I'm not finished because I want dy by dx. So 180t, I can substitute 5p take 2 for t. So 180t is 180 times 5p take 2, which is 900p take 360. And then p is given in terms of x, so this is 900 times 6x plus 1 take 360. Now, more commonly when the chain rule is needed to differentiate a function, we're not explicitly given u, the function of x. So here we've got y equals 2x take 3 to the power of 4, but this bit in the brackets, this 2x take 3, is a function of x. So if we say let u equal 2x take 3, then y in terms of u is u to the power of 4, and we can use the chain rule to differentiate y with respect to x, because dy by dx is dy by du multiplied by du by dx. 4u cubed is 2. So this is 8u cubed. And substituting 2x take 3 for u, this is 8 2x take 3 cubed. In part B, we'll define again what's in the bracket as our u, so we'll say let u equal 3x squared plus 4, then y is u to the power of 5. So dy by dx is dy by du multiplied by du by dx. dy by du is 5u to the power of 4 multiplied by du by dx is 6x. So this is 30x u to the power of 4, and substitute 3x squared plus 4 for u, 30x 3x squared plus 4 to the power of 4. Have another look at these two examples and see if you can work out how we can quickly differentiate functions that are written in this form. So where we've got some function of x raised to a power. Now hopefully you will observe that the power has been reduced by 1. So in the first example, the function of x raised to the power of 4 is now the function of x raised to the power of 3. And similarly in the second example, the function of x raised to the power of 5 is now raised to the power of 4. The function itself, i.e. the bit in the brackets, is unchanged from the function to its derivative. So we've got 3x squared plus 4, 3x squared plus 4. And in each case we've multiplied by the power, but we've also multiplied by the derivative of the function in the bracket. So in the first example we've multiplied by 4 and also by 2, which is the derivative of 2x take 3. In the second example we multiplied by 5 and we also multiplied by 6x, which is the derivative of 3x squared plus 4. Now this is a special case of the chain rule, and you can use this whenever you see some function of x raised to the power of n. Then to differentiate that function, it's n, the function unchanged raised to the power of n minus 1 multiplied by the derivative of the function. So let's work through a couple of examples. We no longer need to say let u equals 7 plus 2x, etc., because we can use this special case of the chain rule. So to differentiate y with respect to x, we multiply by 3. We multiply by the derivative of the function, so 7 plus 2x, that's derivative of 2, and we multiply by the function in the bracket, but reduce the power by 1. So simplifying, this is 6, 7 plus 2x squared. In the second example, again, we've got some function of x in the bracket raised to a power. So to differentiate this function with respect to x, we multiply by n. We multiply by the derivative of the function, which is 2x plus 3. We leave the function unchanged, but reduce the power by 1. And finally, this one looks a little bit different, but if we write it, because it's 1 over x cubed plus 1, we'll write it using a negative power. So this is x cubed plus 1 to the power of negative 1. Now we've got something that looks like the function of x raised to the power. So when we differentiate, we multiply by the power, so that's negative 1. We multiply by the derivative of the function, so this is 3x squared. We leave the function in the brackets and reduce the power by 1. So simplifying, because I've got a negative 2 as my power at the end, that's going to be my denominator. So this is negative 3x squared over x cubed plus 1 squared. Now this example, of course, I could have done using the quotient rule. It's a quotient, so let's try exactly the same question, but using the quotient rule. Let's say that this is u over v. So when I differentiate y with respect to x, remember it's v u dash. Now the derivative of 1 is 0, so when I multiply that by x cubed plus 1, that'll still be 0, so this is 0, take the derivative of the second function, 3x squared, multiplied by 1, that's fine, all over x cubed plus 1 squared, so simplifies to negative 3x squared, x cubed plus 1 squared, which gives us the same answer as when we did the same question using the chain rule. Let's finish up with an example where we're using differentiation to find the gradient of a function at a particular point. So as always, when we're looking for the gradient, we need to differentiate the function, and for this we can use that special case of the chain rule. So dy by dx is 4 multiplied by the derivative of the function in the bracket multiplied by the function in the bracket, reduce the power by 1. So let's simplify this. 8x x squared take 7 cubed, and we need to sub in a value of x equals 3. So at the point 3, 16, the gradient function dy by dx is 8 times 3 is 24, x squared is 9, and take 7 is 2, so this is multiplied by 2 cubed. 2 cubed is 8, so this is 24 times 8. 20 times 8 is 160, 4 times 8 is 32, so this is 192.